Hello everyone. In the second part of our governing fluid dynamics or aerodynamics equation, we are going to discuss on the conservations of mass, or also known as the Navier-Stokes equations. So for the first part of our conservations of mass, we will first look at the balance of our linear momentums, which in this part of our conservations of mass discussions, we only consider that the momentums varies in the linear directions. So it's mentioned in this fluids. It's noticed in this fluid that the equilibrium of force acting on a volume elements of fluid can be described by the momentum equations or momentum theorems, which actually starting or taken principally from the second Newton's law. In this theorem, it states that the time rate of change of momentums of a closed volume will be equal to the sum of external force acting on the of the volume, and this is actually equivalent to the mass multiplied by the accelerations of that fluid particles in the control volume. So if we can remember that the Newton's second law, where the summation of force equal to ma, which is actually can be written as the force that is multiplied by the rate of change of the velocity in time, which is given by the dv over dt. And this equation can also be written according to equation number one here, which is by taking the material derivative of u dv and of rho by taking the material derivative of the mass and multiply by the u to get the momentum. So if we expand this equation number 12 here for the dv over dt and the volume integral of rho u dv, then we can rewrite this equation for the momentum equation, which is given by the volume integral of rho of del rho u dt plus the divergence of rho u. Then this is actually equivalent to the equation number 13 as shown in the slide here. The summation of force in fluid dynamics or in aerodynamics may came from the two sources, which is from we know as the body force, and also the second one is contributed from the surface forces. So let me first look at the contribution from the body forces. And body forces here are actually the forces with a long range of influence which act on all material particles in the body. For example, the Earth's gravitational field. So if we can consider that we take one fluid domain or control volume. So this is our control volume, and we supply the air into this control volume, and we imagine that the air is actually contained of many particles. So for each fluid particle, it contains its own mass. So if we add all the particles in these control volumes, then it will give actually the mass of this particular volume of size, let's say dz, dy, and dx. So under this gravitational field, the mass that contains in the whole control volume, if it's under the gravitational acceleration, then we can get it as the mass multiplied by g is actually will give the mass of force that contributed from the whole control volume that we have here. So the gravitational field strength, which is given by G, actually this is a bool G actually refers to the vector of gravity accelerations in all directions of our coordinate system, acts on every molecule in a fluid particle. So in this case, we can imagine for every single mass, it contains its own mass and also under this gravitational field. If we take for the whole control volume, then the force due to the body force, which is equal to the gravitational force, which is a constant value, and then we multiply by the summations of the mass for each particles. Then we will get G multiplied by M. For the sake of obtaining body force, which is maybe influenced by the gravitational field or electromagnetic field, and these two type of field in general will be represented by vector k. But in our course, we just considering or dealing with the gravitational force only. So our k vector is actually refers to the gravitational acceleration, and it is can be represented by the delta f over delta m. For example, if we take the limit of m, which is small enough close to the zero. So for the sake of obtaining the body force, and the gravitational force is known to be proportional to the mass of fluid, which is given by df over delta m, by taking the limit of delta m, which is small enough close to zero, and it is can be represented by vector k, where in our case our body force is purely contributed from the gravitational force. So the vector k can also be represented by the vector g as shown in the equation number 22. So for surface force, this surface force can appear in the form of electromagnetic field, centrifugal force, pressure, viscous force, and etc. here. So the surface force are exerted from the surrounding fluid, or more generally from other bodies on the surface of the fluid body under observation. If we take example of one control volume that in the form of a cubic shape, something like this. For one cubic control volume where we have the fluid that passing through this control volume, then this for one cubic control volume, it has 6 surfaces or control surfaces. So if we consider a small control surface, or we take control surface of this on the top of our cubic control volume, and the size or the area of this control surface is just ds, which is equal to dx multiplied by dy in terms of the length. Then the force that acting on this surface, small surface area ds that we consider here, will be equal to df, or we can take it as df as well. So this is what is mentioned in equations number 23, where all type of surface force can be represented by the vector t. So the vector t here actually can be contributed from the pressure, and it can be contributed from the shear stress. It can be contributed from centrifugal force or electromagnetic field, and it's just the force per unit surface or area of our control surface. And we remember that the summation of force are equal to m dv over dt. So for the summation of force, as we discussed just now, it came from the two sources, which is from the body force and also from contribution from the surface forces. So if we take the balance from the previous equation where we have d over dt, then we have the volume integral of rho u dv. So this is our momentum ma. Then this is equal to the summation of force that we have defined or derived earlier in equation number 24. So if we further work on this equation number 25, then actually we can rewrite the similar equation in another forms of the equations, which is as represented by equation number 26, where the similar equations of the conservations of momentum can also be written as the volume integral of del rho u dt plus the surface integral of rho u un ds. Then is equivalent to the contribution from the body force and surface forces. So considering that we are dealing with a purely steady state condition, where the flow is considering doesn't change in times, then we can take that the first term on the left hand side of our equation, then we ignore this part of the equation, and considering that we are it's not influenced much by the gravitational acceleration, so the contribution from the body force can also be ignored. So the only terms that left in our momentum equation is just this rho u unds, which is equal to our contributions of force from the surface of forces. Now let's look at one example, which is how we can apply our momentum conservations of equation in order to determine the drag force that generated by these two-dimensional wings. So we know that the fluid with constant velocity given by u infinity and the density of air given by rho pass an infinitely long symmetrical airfoil body. So that means our airfoil, if we look at it in 3D, it will be spanning to infinity. The flow direction coincide with the symmetrical axis, and the only body force is then the drag force, which is given by d, and the drag which is in these directions. Downstream of the body, a wake flow is generated where the velocity now has changed from u infinity until has changed from u infinity to this the flow that we represent it by u1 in x1 and x2. X1 here actually refers to the x-axis, and x2 actually refers to the y-axis. Then with a given the ratio of the velocity between the outlet and inlet, then we actually are asked to calculate or to estimate what is the drag force per unit depth that is acting on the body. We have the air entering this control volume with a uniform velocity of u infinity, and leaving these control volumes with the velocity which is given by u1 and as a functions of x1 and x2. So in this case, in order to solve this particular problem, I think we can label our system according to this A, B, C, D, which is to refer to the surface that we are going to consider later. On the body, we have the surface B, which is referred to the surface on the body. Taking the momentum equation that we have for a steady state problem, we have rho u dot n ds, which is equal to the integrations of the contribution from the surface of forces, and we integrate all over the control volumes. And at this stage, it is very important as well to give the or to draw the directions of unit normal to the surface. For each surfaces, we have 4 surfaces: AB, BC, CD, and DA. So the unit normal is always acting normal from the surface, and it is pointing outward of from the control volume. And from this stage, where these equations will be integrated all over the control of surfaces A, B, B, C, C, D, and we come back to the A to close our control volumes. In this momentum equation, the terms T here actually refers to the stress vector, and often can be represented by negative P multiplied by unit normal on each surfaces. If we expand this the right hand side equation for the stress tensors equation, then we can write this the integrations of surface tensors ds for all over these contour surfaces from A, B, C, D, and then we have also the integrations of these stress vectors on the surface SB or on the surface of our wing. Thus, we know that the surface on the wing in terms of the pressure may varies according to the shape of the wing itself. But on the surface of the control volume, the pressure may be almost constant. So in this case, then we can write that for the surface integral for all over the control surfaces, then the term T here can be substituted by the pressure and the unit normal multiply the control surfaces of each control surfaces from A, B, C, D, and then add with the contribution from the forces that acting on the surface of the wing. If our control volume is subjected to constant pressure, then the integrations all over the control surfaces for this part of our equation will result into no resultant force due to the closed surface of our control volume. So they will cancel out each other. And the integration of the second part on this equation is actually referred to the force by the body force on the fluid inside the control volume, and this equal to the opposite force by the fluid on the body. So this term here actually will refers to the how much the force that is generated by this wing. And this is in our case we only have the drag force, then this term here will refer to to the drag force, and this value is opposite to the directions of the force by the fluids on the body. So we have the negative terms should be negative sign should be applied to this Ft. So thus we can rewrite our momentum equation for this particular problem, which is can be written as Ft, which is the force on the body, which is equal to these integrations of this u rho multiplied by u dot n ds, which is we have to integrate it all over the control surfaces. If we expand our equations, momentum equation that we derived just now, to all over of the control surfaces A, B, B, C, C, D, then we can rewrite these equations as shown here, which is Fd, which is equal to integrations of these right hand side equations of our momentum equations on the each of the control surfaces AB, BC, CD, DA, and also we do the same on these wing surfaces. Knowing that on AB, CD, and DA, where the velocity, the x components of the velocity, which is equal to free stream velocity, on the A, B, and CD, we assume that this boundary is are far away from our wing, where the disturbed flow does not influence the velocity on these two planes or on two boundaries. Thus, we can take that the velocity at this position is equivalent to the free stream velocities. And on the surface dA, which is at the inlet position, the terms the u dot n, which is equivalent to negative ui, and on the wing surfaces, the terms u dot n, which is equal to 0. That means there is no velocity on the surface of our wing due to the no slip wall conditions. So this can actually we can use this information and replace it on these to our equation here, where this term will be equal to 0 on the surface AB. The terms u here, which is equal to u infinity CD. So this is we have a u infinity as well, and then on the dA we have a u infinity as well. And then we substitute on the surface dA. We know that u dot n here equal to negative u. Then we substitute this u dot n by the negative u, and then u dot n on the wall, which is this, will be equal to 0. And on the surface BC, which is at the outlet conditions of our boundary, so we have the terms u, which is refers equal to the ui, and then we have u dot n on the surface on the outlet surface of our boundary, which is here again equal to ui. Thus we can further simplify our momentum equations so that we have negative ft. Now we have the integrations of these on the surface AB, so we have u n dot ds plus we have the integrations on the outlet conditions rho ui square ds plus by u infinity, which is on the surface CD. Similarly, we have rho u dot n ds, and then we minus from the one at the inlet boundary conditions. So we have rho u alpha square ds, and then this actually can further simplify so that we have ft now, which is equal to rho u square ds minus bc integration on the surface bc rho 1 square ds, which is the conditions at the outlet, and then all of this we minus by we have the expression here for the integrations on the surface AB. We have u dot n ds plus the contribution from the surface CD. Then we have similar expression u dot n ds for the surface CD. So the integrals in the parentheses, so in the bracket here, actually refers to the continuity equations on the surface A, B, and CD. So in that case, we, in order to obtain the mass flows across the surface A, B, and CD, then we have to calculate the mass conservation equations all over the control surfaces as well. Taking that continuity equation, which is given by rho u dot n ds, and all of this should be equal to 0. So if we develop the same equations and we integrate all over the control surfaces of our control volumes, then we will obtain that the continuity of mass in our control volume will be equal to this rho u dot n ds plus by the integrations from the surface BC multiplied by u dot n ds, and then plus by the one that on the surface CD. We have the same expression here as well, but we are working on the surface CD. And then we have the last one, which is on the surface AD, which is we have the same expression. And all of this should be in equilibrium or equal to 0. So we found that the continuity equation for the surface A, B, and CD, which is equal to these expressions at the bottom here. So applying the same conditions on the surface AB, which is we know that the u dot n on the surface AB, which is something that we are going to determine later, and on the surface CD as well. But on the surface DA, we know that the u dot n, which is equivalent to the negative u infinity, so negative and negative, we can cancel it out, and we have the contributions from the surface BC here, which is at the outlet, and DA here. So the u dot n at the outlet, which is we have a ui. So if we take our geometry again, where the total height of the geometry, which is given by h, and then our wing is located at the midpoint here, so we have half of the h to the top and half of the h to the bottom. So at this position, if we take these ways of our dimension, so here will be 0, and then here will be positive h over 2, and this position will be negative h over 2 in terms of their geometrical coordinates. So in that particular case, we can write our equation that we obtained from the momentum equations, and we substitute the continuity equations for the surface A, B, and CD into the momentum equation that we generate just now. So we should will be able to come up with the new set of equation, which is given by FD, which is equal to rho u square h minus, we integrate from the surface B to C, where in this case we have rho u 1 square, and then we integrate in the vertical directions x2, and then we minus by the rho g, then we minus by the rho u infinity square h, and then plus by rho u infinity multiplied by again the integration from B to C for the u I dx 2. So if we solve this equation, then we can further simplify this equation for the drag force, which is equal to rho u square, and then we integrate the whole equation from the floor to the ceiling of our control volume, which is from negative h2 to the positive h over 2. And then if we rearrange this equation by written it in the ratio of the inlet and outlet and inlet velocity as shown here, then we can have this u over u infinity multiplied by 1 minus u over u infinity, and then this is will be differentiate in the x in the x2 direction. And if we consider that our domain is big enough, so it's spanning from infinity to infinity on the ceiling and the floor, so the similar equation can be written from the negative infinity to the positive infinity of ui over u free stream multiplied by 1 minus u1 over u infinity multiplied by dx2. And we know that fd rho and u infinity square is just a constant, then we can actually rewrite our equations so that it can be represented similar to the momentum thickness that we found in the boundary layer equation. So if I take this from negative infinity to a positive infinity, then we will have this expression, which is the right hand side equation here, which is very similar to the momentum thickness of the boundary layer.